In this tutorial, we are going to learn how to work with complex numbers using Maple. So the first thing we have to do is to open your folder. You will have this prepared file. It's a zip file, so we are going to have to unzip it. In my case, I have to do open with archive utility, but for instance, if you're working with Windows, usually you will have installed a program which is called 7-zip, and then you will do 7-zip and extract here. Why we do that? Because we want to obtain this folder where we have these two files. We need these two files in order for the commands we are going to use to work properly. Okay, so let's open this tutorial. Okay, so we close it. Okay, so let's see how to work with complex numbers in Maple. First thing we have to do is to open this section, zero code, and execute these lines. Execute means you place the cursor wherever you want and you press intro or return. So you go wherever you go and execute. Even though it seems that we are not doing anything, we will need this because in executing this line, we are having some functions which we are going to use to plot numbers. And these functions are not from Maple, we have programmed it ourselves. So now that we have this, we open binomial form, and let's see how to work with Maple and complex numbers. The binomial form of a complex number is just z equal to the real part a plus the imaginary part and the imaginary unit, where the imaginary unit is, we usually write it by I, but in Maple is capital I. So its property is that I squared is -1, and you see that if we say to Maple compute the square of -1, it returns capital A. So whenever we want to use the imaginary unit in Maple, we are going to use the capital A command. Okay. Now, any complex number, you know that it can be represented as a point in the plane. So, and the x-coordinate will be the real part and the y-coordinate is the imaginary part. And here we will use a function which is complex plot to plot complex numbers. So let's define the number 4 plus 6i. Z, to define a number we use colon equal, okay, not just an equal, this is a definition, colon equal, real part 4 plus imaginary part 6i. We execute the line, pressing intro. Remember that you can place the cursor wherever you want, and then we use the complex plot to plot it in the plane, which should be this, how you will plot this complex number in the plane. So it will be the point with coordinates 4, 6. So if you do the plot, then you see 4, 6. If the plot does not appear, it's because you haven't done this correctly. So come here, code, execute the lines again. It's not just looking at them, it's pressing intro at them, okay? And then come here and do the complex plot. Okay, so now first exercise, plot the following complex number, z equal to -1 plus 2i, and plot it. Okay, so now in this tutorial we are going to work with Math1D all the time. So remember that with F5 we changed from Math2D to Math1D, and Ctrl-J, Ctrl-K, or press this symbol here to put more points. So I'm going to be changing the lines. 5. And now let's copy this, because if we copy things, we will not introduce mistakes. So z in this case is -1 plus 2i, capital I, remember. And now complex plot, it should plot the point -1, 2. So -1 real part, 2 imaginary part. Okay. So this is how we define. Now we can delete this with just the delete function in the keyboard. So now you know how to define numbers in polar form, in binomial form, sorry. Let's see how to define numbers in polar form. The idea is that every complex number can be represented by a point in the plane. So another way of representing this number, for instance, is just giving the distance from the origin, which is called modulus or magnitude or length, and then giving also this angle, okay? The angle with respect to the x-axis. Okay, so this would be the argument. So the angle is going to be called argument. So we will have the modulus, or magnitude or length, and the argument. In Maple, it's really easy to compute the modulus and the argument of a number because we have the ups and argument commands. So we make more lines. Remember Ctrl-J, Ctrl-K, or the symbol up above. We define the number, colon equal, -1 plus I, execute the line, and then plot it and compute its modulus and argument. So in order to plot, just because we don't want to introduce mistakes, we just copy complex plot from another section. Complex plot. This is the point -1, 1, which is going to be the modulus. Remember that we have a triangle with length 1 and 1, so this is going to be square root of 2, and the angle is going to be 90 plus 45, 135, okay? Let's check it. ABS of z, square root of 2, another line, F5, argument. Whenever you see that it's appearing the command, you just can press the tab button, tabulator, and then you get it. 3 pi quarters, remember that we are going to be working always with radians, so we just copy this, paste it, multiply it by 180 divided by pi, and we get the 135 degrees that we were saying, okay? So this is the modulus, this or magnitude, this is the argument, and the number in polar form would be square root of 2, argument 3 pi divided by 4, okay? Now, how do we do if we want to introduce a number directly in polar form? So we have the command polar, where we place the modulus and the argument, okay? And it becomes, this is the polar form, how we introduce, for instance, the number 2 pi in polar coordinates. 2 pi, which number is 2 pi? It's magnitude 2, pi means 180, so it's -2, okay? Now we'll see, because this is not simplified, but if we simplify it, you see that it's -2, okay? Polar form, directly, is modulus times the exponential of the argument times the imaginary unit. Don't forget this, the imaginary unit in the exponent. And directly we can write it using the exponential command by introducing the imaginary unit in the argument, okay? So now let's do this exercise. Z is going to be -1 plus I. Using the modulus and the argument, find zeta pol and zeta exp. So, I'm sorry, F5, remember F5 every time. So we do it again. The argument or the magnitude is square root of 2. We already know that. The argument is going to be Control K, F5, 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 F5. So the polar form is going to be polar magnitude, square root of 2, Control C, Control V, and argument, okay? And in exponential form, 2 columns equal, we are going to place Control C, magnitude times the exponential, and the argument, times, don't forget the imaginary unit, because otherwise it's going to be a real number, okay? So in this case, you can see that Maple simplifies the expression, okay? So we simplify the exponential number, we get the initial one, okay? Now, you know how to introduce a number in binomial form, also in polar form and exponential form. Let's see how to convert from one to another. Converting from binomial to polar. We've seen that we can do this by using the ups and argument, since, like we've done here, we compute the modulus, the argument, and we use the polar command. But also you can use the convert command, which directly converts a number in binomial form to polar. So we have z, we compute its magnitude, its argument, And we use the command polar to compute, to put it in polar format. We can also use convert the number to polar, and you will see that we get the same result. So these three lines, these three lines are completely equivalent to this one line. So if we have to do it, it's fastest to use the convert polar form, and here you can distinguish the modulus or magnitude and the argument. Okay. Now, converting from polar to binomial. Given a number in polar form, remember that its binomial form is magnitude times cosine of the argument plus sine of the argument times the imaginary unit. So we can either do it by hand, or also we have this command evalc, which directly converts it. Okay, so we have a number in polar form, which will be the binomial form. Magnitude, if we do it by hand, times cosine of the argument plus sine of the argument times the imaginary unit. Or we can use the evalc command, which directly converts a number in polar form to binomial form. Okay, so let's do the following exercise to practice.
Welcome to VoiceOver.
Sorry. F5, 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 F5. We have in the A exercise, we have to convert these complex numbers which are in binomial form to polar form. So let's define Z1 as equal 1 minus I. And let's convert it to polar. You can compute separately the magnitude and the argument and use the command polar, or directly Z1 pol. We can use the command convert. So we are going to convert Z1 to polar. So the modulus is our square root of 2, the argument minus p over 4. Okay. So this is going to be a number in which quadrant? In the fourth quadrant. So if you do a complex plot of Z1, okay, so we have 1, 1, magnitude square root of 2, and then the argument is going to be minus pi divided by 4 minus 45 degrees. We put a colon so that if instead of a semicolon we put a colon, we don't see the result. Okay, so let's go to the second one. Z2 is going to be square root of 3 as a real part plus 1 times I, okay, the imaginary part. And again, Z2 polar is going to be convert Z2 to polar. And here in this case, we're going to have a magnitude of 2, and the argument is going to be pi divided over 6, so it's going to be a number, we copy this, in the first quadrant, so we now put semicolon in the end. Okay, magnitude 2, argument pi divided by 6. We again place the colon so that we don't see it again. And now the opposite exercise. So from exponential to binomial, so Z3 is going to be square root of 2 times the exponential. If you don't remember how to put it, just go to expression and press the exponential button. And now the argument is pi divided by 4 times A. Don't forget, I, the imaginary unit. In this case, it directly translates it, but usually we have to use the evalc command, okay? And using the evalc command, you see that it's also simplified, okay? 1 plus 1, of course, complex plot of Z3, of course, having an argument of pi divided by 4, which is 45 degrees, and a modulus square root of 2, it's the number 1, 1 in the plane, okay? So we already have this, and the last one is 5 times the exponential of 3 pi divided by 5 times I, 5. So Z4 in binomial form is going to be evalc of Z4. And now that you see that this number, Maple does not simplify it because the cosine of 2 pi divided by 5 is a decimal number, so you can go, remember the context-sensitive menus, you can go to the right click, and approximate using, for instance, 10 decimal places. So this number here, the number having a modulus 5 and an argument of 3 pi divided by 5 is minus 154 plus 475i. So this is the end of this section. So we've learned how to introduce numbers in binomial, polar, and exponential form. And we also know how to convert from one to the other. So let's move to next section, which is, now that we know this, we need to know how to compute, how to operate between complex numbers. We will first do addition and multiplication, and then we'll go to powers and roots. So operations, you have here a table, which I think it will be quite nice for you to remember. Depending on the operation, we need to have the numbers in different forms. So for instance, we can only add and subtract complex numbers if they are in binomial form. This is nice, and this cannot be done, okay? The product and division, it's easier if we have the numbers in polar and exponential form, because in this case it's direct. But we can also do it in binomial in some cases, which is easier. If we have the numbers in binomial, usually we will do the product also in binomial, because we will not want to convert them to polar and then again do the product and then reconvert again. Powers, they are really easy. We have the numbers in polar or exponential form, but they can also be done in binomial if you like. But then, in order to compute roots of a number, you can only do it in polar or exponential. You cannot compute the roots of a number using the binomial form. So in this case, if you're given a number in binomial form, in order to compute the roots, you will have to first convert them to polar. Okay, so let's now see addition, subtraction, and product division, how we do that in Maple. Addition, it's really easy. We define two numbers, and then the addition, in order to add, you add the two real parts and two imaginary parts. So the result is going to be 3 plus 8i. But we can directly do it using the plus operation. So Maple knows how to add two complex numbers without having to do it by hand. Okay? Multiplication, imagine that we have already said that it's easy to do it in polar form. How we multiply two numbers in polar form? We have to multiply the magnitude. So the magnitude of the product is going to be 2 times 3, 6. And then the argument is going to be the addition of the two arguments. So the magnitude is multiplied, but the arguments are added. Sorry, product. Let's put prod. So the resulting number has a modulus 2 times 3, and the argument is 1/2 of pi plus 1/4 of pi. You can also do the product by using Z1 times Z2, but then you have to simplify the result so that you get the same. Okay? So let's do this following exercise. Remember to do F5 every time. Exercise, compute the addition of the two following numbers. So Z1 is going to be, we can introduce them in polar form, modulus 2, argument, pi over 3. We could have also introduced this in exponential form. It doesn't matter, so it's 2 times exponential of pi divided by 3 times the imaginary unit. Okay, so it's the same thing. If we do this like this, you can see that it's directly converted to binomial, but otherwise, once we have Z1, we should use Z1 binomial, Z1 to convert it, okay? Now, the second number, Z2, it's polar, 4 pi over 2. we convert Z binomial to evalc Z2. So we now have two numbers in binomial form, Z1 bin and Z2 bin. So now we can add them. So it's going to be Z1 binomial plus Z2 binomial. We cannot add two numbers in polar form. Okay, Z1 plus Z2. You can see that Maple does not do the addition unless we at the end translate it to binomial. Okay, so addition in binomial form. Now let's see the product. So now Z3 is going to be 1 plus 3i. Z4 is going to be 2 plus 2i. Okay. In order to do the product, we could do that directly in binomial form. In this case, it would be easy. So we would go like this. There is not a correct Maple statement, it's just for you to see. So we would proceed to do a product, just we do it like in real numbers, 1 plus 1 times 2, 1 times 2i plus 3 times I times 2 plus 3 times I times 2 times I. Then we have 2 plus 2i plus 6i plus 6i squared. Now 6i squared, so we have 2 plus 8i minus 6, because 6 times I squared is minus 1. So we would get minus 4 plus 8i. Okay, let's put this symbol here, which means that it's a comment. So Maple is not going to execute it. So remember to put it. And let's see what happens if we do Z3 times Z4. Maple directly computes it. However, we should also know how to do this in polar form. So let's do that. Z1 polar is going to be convert Z3 in polar form. Now you see that this is not quite easy to do that. Sorry. F5. Z4 pol is going to be convert Z4 to polar. 5. And now once we have the product, so we would do polar times polar. This would get that the modulus would be 2 square root of 2 times the square root of 10, and the argument is the addition arctan of 3, the arctangent of 3 plus pi divided by 4. In order to do the product, we have to simplify it. Okay, so you can see that the arguments are added and the magnitudes are multiplied. And then if we convert it, let's remember Control L, equation 418. If we convert it and we just approximate it numerically, you will see that we get the same result, minus 4 plus, and this is due to rounding errors. Okay, so propagation of errors, this should be an 8i. Okay, so in this case, it was easier to compute the product in binomial form, but usually, if you get the numbers in polar, it's straightforward to compute the product. Okay, so let's remove these two lines. Now we know how to compute additions and multiplications. Let's see how we do with powers. Again, powers, you have the de Moivre's formula, which tells you that if you have a number with magnitude r and argument theta, then if its nth power, it's the modulus, you have to make the power to the n, and the argument you are going to multiply by n. So remember that the modulus has a power, but the argument has a product. So if we have a number, how we square this number? 2 to the square is 4, and we multiply this by 2. So it's 2 to the square, 2 times pi divided by 5. We simplify it. You can do it by hand or simplify z squared. And then the cube is going to be 2 to the power 3 times the argument. And if you simplify directly, you could compute z to the power 3, but you should also know how to do it by hand. Okay? Exercise. Compute the fourth power of z. So let's first do it in polar form. Z pole, it's going to be convert z to polar. And now z pole to the power fourth, it's going to be polar. What do we have to do with the modulus? If we are computing the fourth power, we just take the modulus here, power 4, and we place 2 times square root of 2. Okay, so it's the initial magnitude to the power 4, and with the argument, we have to multiply it by 4. So in the end, you get 324 pi. Pi, remember, that is the negative part of the real axis. So this, if we convert it to binomial, we would get minus 324. Okay. Now, in this case, we could also have done it by hand. Using binomial 4, because z to the power 2 should be 3 plus 3 times I. This can be done by hand, okay? And you will get 18 times I, and then z binomial to the power 4 is like it's the same like squaring again the square. So you could get the same result. In this case, it would have been faster to compute the squaring binomial and then a square this again. Okay, so it's 18 to the power 2 minus 1 due to the I square. But you should know how to compute powers either in polar or in binomial form. Now this is just a picture, okay? So how do the powers plot, or how are the powers represented in the complex plane? So you will see that as we increase the power, the modulus increases, and the argument between any of them, you can see that is the same. So the argument is always increased by the same magnitude. Why? Because we have the initial angle, twice the initial angle, 3 times the initial angle, 4 times the initial argument, 5 times, 6 times. So to go from one power to the other, you always add the initial argument. Okay? So the arguments are always equidistant, and then the modulus is increasing if the initial argument is greater than 1. Okay? Now, another exercise. This would be easy. We are going to use maple with its all potential, so z squared plus z to the power 4 plus z to the power 8. Directly maples computes this. So we don't have to convert to polar or even do it by hand. Maple directly converts it. Okay? So let's see, now that we know how to compute powers, let's see how to compute roots. So every complex number has n nth roots. So it has 2 square roots, 3 third order roots, 4 fourth order roots, okay? 5 order roots. And how do we compute them? So imagine that we have an initial number z, which has a magnitude of r. The magnitude of the n roots is just the n root of the magnitude of z. Okay? And the arguments are, the first argument is the initial argument divided by n, and then you have to add 2 pi divided by n. So let's see in a simple example. let's start with I plus A. Remember that we can only compute roots using polar form, so we convert it. The initial magnitude is square root of 2. If we want to compute third order roots, you can see that all the magnitudes are going to be the square root of the initial square root of 2. So all of them have the same magnitude, which is 6 root of 2. And then let's see the arguments. The first argument is pi divided by 4. So if we are computing third order roots, we have to divide it by 3, like this. Now we have the first argument, which is pi divided by 12. And all the 3 rods are going to be equidistant in arguments. So if the whole circle has an angle of 2 pi, we are going to add 2 pi divided by 3 to the argument we have above. So it's pi divided by 4 plus 2 pi divided by 3. And the second one, we are going to add 2 times 2 times. Okay? Now, if all the modulus or magnitudes are the same and the angles are equidistant, you will see that they are placed on a triangle. Okay, so you compute the first argument dividing the first argument by 3, and then since you have to have 3 different pieces of cake, the distance is going to be 2 pi divided by 3, 2 pi divided by 3, 2 pi divided by 3. So if I add here again 2 pi divided by 3, I'm going to end up having this one again. And now, just to check that we've done it correctly, if we put the power 3 of the number of the roots, we get always, in all the cases, the initial one. So in order to check that we have done it correctly, you just have to compute the power to the 3 and see that you get the initial one. So let's do this last exercise. F5, 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 F5. Okay, so the initial number we are given is 1 minus square root of 3 times I. And we are asked to compute the 5th or the 5th order root, the 5th order root. Okay, so, sorry, let's put Z here. Sorry, I cannot go here. Oh, Z. Let's compute the polar form of this number. Convert it. So we get a modulus of 2 and an argument of pi divided by 3. Which is going to be the first root. So it's going to be put in polar form. The modulus, so we take the initial modulus, which is 2, and we have to do the root of order 5 because we are computing 5th order roots, okay, the exponent. And now the modulus is going to be the initial magnitude divided by 5. So the first root is going to be this one. Which is the difference between the first root and the second one? The difference is that they are going to be placed in a circle and we have 5 pieces of cake. So between one and the other we have an angle of 2 pi divided by 5. So we add 2 pi divided by 5. This is the second one. And what about the third one? So we take the second one and we add again another piece of cake. Okay, you can remember this like pieces of cake. Then you will see the Z4. Remember that we don't change the magnitude. We just add 2 pi divided by 5. And the last one, because we have 5 roots. Okay, so this one.
Welcome to VoiceOver.
Sorry again.
VoiceOver speaks to script.
Wow. Same magnitude. We add again another piece of cake. Okay. Now let's do a plot. This is an advanced thing. We copy this plot. So If you don't know how to do it, it's okay. We paste it, and instead of plotting 3 numbers, we're going to add 2 more, 4 and 5. And here the same, the 3, I copy 4, and I change it to 4, 4, 5, 5. Oh, something is wrong. As you can see, we should get something here, okay? So let's see what is wrong here. Okay, Z3 is not executed. You can see that I have the line, but I didn't press return. Now that we have Z3, now you can see that they are placed in a regular polygon. Okay, don't know why we are not plotting this button here, but you have another one here. Okay, therefore 1, 2, 3. Okay, because I have a 4 and a 4, 5. Now the plot is correct. Okay. So let's do the other exercise, which is this one. I'm going to copy here so that we can see it. Here we have to compute the square fourth of the root, but then we also have a power 5. So we start with 1 minus I. We compute z to the power 5 with z to the power 5. Now we have to convert this number, sorry, Control J, Control K. We have to convert this number to polar in order to do rods. So ZP5 polar is going to be convert ZP5 to polar. So now we have computed the power 5. Now we have to compute fourth order roots. Okay, so Z1, it's going to be polar. Since we are computing fourth order roots, we will use the root order 4 of the initial magnitude. Comma, and the argument, the first argument, sorry, is divided by 4. So we make the root fourth of the initial magnitude and we divide the argument by 4. The second one, so the second one, we copy this again. Same magnitude. And how many pieces of cake will we have now if we have fourth order roots? We'll have 4. So the full pie should be divided by 4. This is the second one. 5, 5. What about the third one? So we are going to add again another piece of cake. And the last one, you always take the previous one and again add a piece of cake. Okay. Now that you have it, you can, if you want, we can also make a plot. And what do we have to obtain? Remember that we have to obtain a square in this case. So we remove Z5 and we remove Z5. And you see that we obtain a square. Okay, so when I'm talking about pieces of pie or cake, it's because you have to divide the full circle into 4, in this case because we are computing fourth order roots into 4 places. So with this you have seen all the things you need to know about complex numbers and Maple. And if you want, I suggest that you do the following exercises. And if you see that you can do that, is that you have understood or perfectly understood the lesson. So see you next time.